Hi, my name is Zoe Turner, and this is my Lab 5. And in this lab, we choose our own adventure. And in this adventure, I chose a Slinky drop. And in this lab, we analyze the motion of a falling Slinky, and we create a model in Tracker and GlowScript. And at the end of this presentation, I will compare the two models and analyze and explain some of the physics that happened behind them. So some key concepts that we have to know before going into this lab. We have to know Newton's second law because it updates our final velocity. And in our code, you'll see we have to keep updating it at every position to have accurate data. We also need to understand drag. And drag is in the opposite motion of the falling Slinky, which means it can slow down our Slinky. And if this isn't taken in consideration in our code, that's how data can be severely screwed. We need to have our unit vector because how I have the data, or not the data, how I have the Slinky falling, it's in the pointing up in the y direction. And we need our position update formula because without position update, we can't really find the updated velocity. So here are some initial conditions. I have the mass of the ball, and I have the ball's position. And we got this position from our tracker. And as you look down, we have our gravity near the Earth's surface, and we have our proportionality constant for our drag. And the only reason why this is so big is because in the original video, it was in slow motion. So we have to sort of blow up the proportionality constant so that it can be accurate to our actual model. So, and more into this code, when time is less than 5.4 seconds, we have to analyze all of the different forces. And we do this because it is essential in our ball's velocity update formula, which is Newton's second law. And here we analyze weight and tension to create that net force, or F net. And as we pass the 5.4 seconds, and while t is still less than 8.3, we need to analyze drag. This is when drag is necessary because the Slinky at this point is falling towards the ground. And so we have to analyze drag so we know how much it is essentially resisting. And we also update Newton's second law, of course, and the drag and the weight force is calculated in the F net, which the F net is used to update ball's velocity. Now, here's a comparison between Tracker and our GlowScript data. We can see it is extremely similar. The red line is Tracker and the blue line is GlowScript. The small discrepancies could be some other forces that we aren't looking into that create only a small sudden change. So that's why you can barely see the blue line under the red line. So what does this mean? Why do we do this? Well, the bottom of the Slinky stays stationary until the top of the object falls on the Slinky. So what does this mean? This means that at between from 0 to 5 seconds, the Slinky was motionless until the top of the Slinky falls on itself and then it starts to fall. So the model in our GlowScript, it has the same predicted outcome as our Tracker data. This is because the tension in the Slinky is pulling upwards and it's balanced with gravity until the entire Slinky was compressed. After the Slinky is compressed, it falls to the floor, which is why we have this comparison. Well, you can see how the line is straight, but once it starts falling towards the floor, it starts to go down towards the -2 meters. Well, thank you for watching my lab. My GlowScript code is in the description, so if you ever want to watch or look over it, you can tap the link there. And there's my cat. Bye!